Welcome to this segment that I will discuss here the idea of torsion of thin walled sections. And what we will discuss are possibilities for torsion of sections that have a very thin wall and that can be either closed completely, continuous, or they might have a slit. Obviously, if they have a slit, then the angle of twist, you would understand that it should be very large and it would be easier to apply torque. So we wanted to develop the basic formulas that allow us to calculate the shear stress in thin-walled sections. And we will introduce an idea of what is called shear flow that is used to determine the shear stress in these sections. So let's consider now a section that has a general shape. That general shape could be represented, as you can see here, and the thickness could be also variable along the arc length. So the arc length here is measured as S, and if we just take an element of that section, so this section this is looking down on a section, so the paper is like a cross cut into a tube, and the tube goes into the Z direction that we are considering. So here we are going to take an element, and this element would be ds, and there's an area here that is carrying a shear stress. And then let's take the center of that section here as O, and let's connect the beginning and the end of that element with the two rays coming from the center. And let's also consider that we will look at, let's say, the area that is of this triangle here. If the distance from O to the S is R, this is also approximately equal to R on the other side. So the area of the triangle is approximately equal to 1/2 times R times ds, and that is the area. We're going to call it dA. So if we are considering some kind of a vector representation for this, then we would say that ds cross R is equal to 2 times dA, where dA is a vector that represents the area that is coming out of the paper. So we also assume that there's a in this little area here, there is a shear stress tau that is to be determined in the theta direction. So the angle of rotation is theta, and on the z plane. So the plane that we would consider is the z plane. So tau theta z, and we will also define the force per unit area per unit length as equal to Q. So this is by definition we're going to call it Q. So it's a force per unit length, and in magnitude it is equal to tau theta z times T, because it's per unit length. So with this we're going to call this Q the shear flow. So Q is now given the symbol shear flow. So if we consider equilibrium, we're applying a torque on that section, then the amount of torque taking up by the small area that I described here. This is carried by the forces in this area would be equal to the Q, because it's per unit, the force per unit length, times the length, which is ds, cross r, because that gives us the moment, and it's a vector, which is, we call it torque, and this torque is just moving outside the plane of the paper and in the z direction. So this is the torque balance on that small area. Now if you want to apply a torque that is to be resisted by the shear stress in the total area, we just have to integrate this equation to get the total torque. So if we consider now by integration, so before we do the integration, we'll write it now in scalar form. So it will be Q times 2dA, because that's what we found. ds cross r is 2dA. And if we do a line integration, so if we integrate over the closed line, so this is a closed line integral, and it should be equal to the closed line integral of 2q dA. And since we are considering a situation where q is constant in the cross section, we can take it out of the integral, and therefore we would have 2q times a, which is the total area that is enclosed by the curve, and that gives us finally one of the two formulas that are useful for thin sections, that q is equal to T over TA, which is known as Brett's formula. Notice that A is, we're going to call it A sub m, which is the mean area. And the mean area, we're going to define it so that we have the cross section exaggerated here. Then the mean area would be the area of the mid. If we draw a contour that is midway between the out and the in, then the area that is subtended by this contour, which is this area here, is A sub m, or the mean area. So this will be, to be specific, it will be the mean area. Also, if we want to compute, now we figured out how to compute the shear flow by Brett's formula, that Q is equal to T over 2A sub m. And from Q, we can always find the shear stress, because the shear stress is Q over T. So Q would be constant in the section, in the thin section, but the shear stress itself can vary depending on the thickness, the local thickness of the section. So this is one formula. Another formula is that we wanted to find the angle of twist. And in order for us to find the angle of twist, we just have to use an energy principle. So we're going to apply a torque, and then the section is going to twist, and the work done in that process is 1/2 times the torque times the angle of twist. Just like 1/2 times the force times the distance is 1/2 times torque times the angle of twist. This energy has to be stored in the whole volume as an elastic energy. So if we equate the work done to the elastic energy stored, we should be able to get a formula for the angle of twist, and that's what I'll do here. So if I write this here, and the angle of the energy is 1/2 times T times theta. So I'm going to write it as theta 1. This is per unit length, and this is equal to the volume integral of the elastic energy, which is tau theta z squared over g. So this is the energy per unit volume times the volume. And now I can write it as 1/2 1 over 2g and then instead of tau, I have q over t squared dv. And note that I can write that as, if I write this as 1/2 t times theta 1. So since q is constant, I can write dv as t times ds, because times 1, because this is per unit length in the z direction. And therefore I have I can take the g on the other side and write this equation as t times g times theta 1, and I cancel the 2 with the 2, and then this will be equal to the integral. This is now integral over of q squared over t squared, so I'm going to write it as q times q over t, and then the dv, I'm going to write it as t ds. And in fact, this will be q over t, so this t goes with the t, and if q is constant, then I can take this out of the integral. So knowing that q, notice from the previous formula that we have q is equal to t over 2a, so q equals t over 2a, so we're going to use this. And when we take it out, then we have t over 2a mean integral of q over t ds, and this is a closed line integral, is equal to t times g times theta 1. So the t will cancel out, and finally we have another equation that is useful for calculating the twist angle. Theta 1 is equal to 1 over 2 mean area times the shear modulus times the closed line integral of q over t ds. If q is constant in the cross section, I can take it out, and this will be q divided by 2a mean g integral of ds over t. So if we have a variable t, then we have to integrate over the section. If t is constant, we can pull it out of the integral, and the integration of ds becomes actually the perimeter of the section. So in this case, we can write a final formula that we will use as theta 1 is equal to t times L sub m. This is the perimeter, mean perimeter, over 4 times a sub m squared times g times t. And I think I notice here that we have to have, when we substitute for q of t, then the a sub m becomes a sub m squared, and then you bring in another factor of 2. So that's basically the final result that we are going to use in our calculations. And now we are kind of ready to look at some applications and some examples. So let's see what type of examples. So I'm going to show you a few examples from the notes, and then we'll just go from here. So if we look at the notes, it's a similar approach where we have, this is ds in here, this is r, this is the area, dA equal to 1/2 of r ds, and this is the median line that I was talking about. So when you do the integration, you get tau equals t over 2a sub m times t. And we proved now that theta 1, which is the twist angle, notice is radians per unit length, is t lm over 4 g am squared times t. Everything has to be done with the median line. So let's take an example here. And the example that we're going to take is like a square tube, and it has inner and outer dimensions. So we have to figure out the area that is enclosed by the mean section area, and also the mean perimeter of that cross section. So these are two important quantities that we can use. So if we look here, we find that we wanted to have, this is 40 inches long and fixed from one side, and then we're applying a torque here, and the torque that we're applying, we wanted to find the maximum value of the allowable torque if the maximum allowable shear stress is 11.5 KSI, which is 11,500 PSI. And then we're given the shear modulus of the section. The wall thickness is 1/8 of an inch, and it's 2.5 by 3.6. So the calculations are, first is we have to find A sub m and L sub m. So A sub m, we subtract half of the thickness from both dimensions, you get the area. And here you get the perimeter with the subtraction of half of the thickness from each dimension. And then the torque allowable would be just 2 A sub m T tau, and tau is the allowable stress. So we get an allowable torque of 23,730. And the angle of twist, note that the total angle of twist is the angle of twist per unit length times the length. And the length is 40 inch. So that's important. So this 40 inch here. And then we apply the formula for theta 1, and we obtain the value in radians. And when we convert radians to degrees, multiply that by approximately 57 degrees, then you get 1.62 degrees for that twist. So it's a very small twist angle that corresponds to the allowable shear, the allowable torque on that steel box. So let's go beyond that and see what we can learn if we have a comparison. For another example, we want to compare the shear stress in a circular cylindrical tube with an outside diameter of 1 inch and an inside diameter of 0.9. So the thickness of the wall is 0.1 inch. And we can predict the shear stress in two ways. One is by the strict formula of solid cross sections, which is TR over J. And the other one with using Brett's formula for thin sections. So let's compare those. The key here is J is the polar moment of inertia, has to be the difference between the polar moment of inertia of the outside minus the inside. So it gives us 1 to the power 4 minus 0.9 to the power 4. And here we use the mean section area. So the mean between the inside and outside is 0.95, that's square. And therefore we get 14.1. So the difference is really very small, is less than 5% if we just do a quick estimation using Brett's formula, as you can see here. Now the last topic that I'm going to discuss now is a topic that is interesting, is that if I have a cross section that has thin walls, but instead of closed, it has a slit. So let's see what we can do with these cross sections. So here we're going just to use design formulas without proof and compare the results to the closed sections. So if you have an open section would be characterized by two numbers. C is the thickness of the wall, and L is the length of the median perimeter. So the median can go straight like this, or can go around, or can go in a U section, or a L section, or a Z section. In all of these situations, the shear stress, so we have only one formula here instead of two. One formula that relates the shear stress to the torque, and also relates the angle of twist per unit length to the torque. So tau is equal to G theta 1 C. C is the thickness, and this is equal to 3 times the torque over LC squared. So we note here that the shear stress is like the torque divided by a geometry or a dimension to the third power, because you have length L and then C square. So compare this to before, and that is kind of, it should be consistent with Brett's formula, that the torque divided by first power in length, second power in length, so it's a cubic in the length itself. So in that case, we would have for an open section, it will be C squared times L in the denominator. So let's do some estimations here and observations. So the first observation is that the torque is inversely proportional to C squared. So as it gets thin, then the shear stress increases dramatically. And also the angle of twist, you can see that it is angle of twist per unit length is the torque divided by C cubed. So as the section gets thinner, then the angle of twist rises by the cubic power of the thickness. So it becomes very, very flexible, and it can twist quite readily. So let's look at example here. We see that you can verify for yourself that if you have a thin round tube with and without slit, with the if you have the wall thickness ratio to the outside diameter of 0.1, so you can use the formulas we developed, you see that the stress in the slit is 12.3 times greater than without the slit, and the twist with the slit is 61 times greater than a section without the slit. So let's finalize that and take an example. We're going to take another example here where we have a section that is has a rectangular cross section, and we're going to use two formulas, the original one that we use for a solid section, and then the approximate ones that we developed based on the ideas of Brett's formula extended to thin section, open sections. So here we have the cross section is 1 inch by 1/8, and we have a torque, and maximum allowable shear again is 11.5 KSI. Shear modulus is given, and what you want to do is that if we're given that, we want to find the corresponding torque and the to the allowable shear stress and the angle of twist in degrees, and we want to use the solid cross-section formula and the formulas that we developed for the thin-walled open sections. So the thin-walled open section is the torque is equal to LC squared over 3 times tau. That gives us 59 pound-foot inch. And the total angle of twist is per unit length times L. Per unit length is tau over GC, and that gives us 5.5 degrees. If we think about this as a spring, we can say that the spring rate is defined as the torque divided by the angle. That gives us a spring rate of 624 pound-force inch per radian. Now, if we go back to the solid cross-section formulas, then we can use this formula, find that the torque is 55.7 and the angle of twist is 5.6, and the spring rate is 574 pound-foot inch per radian. So you can see that the equations give us a value of 7.5% higher. So let's see here, this is, let's say, 59.9, this is 55.7. So the thin wall approximation is a little bit less conservative. It gives you about 7.5% higher, and again this equation here gives you for the angle of twist 5.5 versus 5.6. So that's not a very big difference, and it shows us that we could readily use the thin wall approximation based on Brett's formula and the formula for the angle of twist, and then we extend it to situation with open sections. Once we kind of determine that the thickness of the wall to the main dimension is at least 1/10. So if it is, or at most 1/10. So if it is 1/20 or 1/30, then the approximations become even more relevant and easier to apply. And we'll see what we can develop for other additional areas of stress analysis in